Jena. Okay, and we are going to learn something about approximating convex bodies using multiple objective optimization. This is probably the reason why we have vector optimization people in the audience. Welcome, everybody. And the body is yours, Andreas. Go ahead.
Yes, thank you very much for this introduction, and thank you very much for the invitation to this webinar. My topic is the connection between approximating convex bodies, convex sets, or also special convex sets like polyhedra to multiple objective optimization. And this is a summary of several research papers from the last, say, 7-8 years. And here is some outline. I would like to discuss this topic on different levels. So many things are can be explained on a polyhedral level. So I want to speak about polyhedral convex sets and multi-objective linear programming and the connection between it. The most general level is convex sets and multi-objective convex programming, and in between it is maybe also interesting to say some words on special convex sets, spectrohedral shadows, and the corresponding optimization problem is multiple objective semi-definite programming. I will start with the polyhedral setting and then go ahead to the more general settings. And you will see that the idea is actually the same. It's a very simple idea, very simple connections between approximation of these sets and the corresponding multiple objective optimization problem. So let's start with a setting for polyhedra. Many concepts are based on projection, and therefore I want to introduce the so-called P or projection representation of a polyhedron. So the idea is the following. Here we have linear inequalities, and the projection is here in this matrix M. We have a linear mapping, a matrix, and we project a polyhedron in the X space to some other space, usually a lower dimensional space. And in this reformulation, you can see the idea of projection. If we introduce another variable y here and we set mx to y, then we have here a polyhedron in the xy space, and we project it down to the y space, which is RQ here. The H representation, also called inequality representation, is a special case. If we set M to the unit matrix, then we obtain an H representation. And what is also very common is the so-called V representation. This is a representation by points and directions, or sometimes also called a vertex representation. And also the vertex representation is a special case. And what you see here is a kind of generalized convex hull. In the matrix V, we have the points. Here we have the directions in the matrix D. And in the matrix L, we have some kind of linearity directions. If the linearity space of our polyhedron is non-trivial, it is preferable to use some extra matrix to represent it. So this is polyhedron in the space of variables y, lambda, mu, and eta, and it is projected down to the y space. So that means a P representation generalize both H and V representation. And to get some flavor what polyhedral projection means, I have some initial example here. When we start with a three-dimensional polyhedron, a tetrahedron, the question and we want to compute the shadow, the two-dimensional shadow, what we see here in the plane. Then the question is, can the result of a projection be more complex? So at least in my case, it was so that my intuition was wrong in this case. I had the idea that projecting a polyhedron down to a lower dimension leads to an easier polyhedron, but this is not the case. And we have here the tetrahedron. This is described by 4 inequalities. And when we add another inequality, so then we cut off a vertex here by this 5th inequality. And after cutting off this inequality, we have in the original three-dimensional polyhedron 5 inequalities, but the projection has 6 inequalities. So this is maybe the easiest example showing this effect. And here is a more complex example. Here we start with a 729-dimensional unit cube. And this cube has this number of vertices. This is maybe more than the universe has atoms, but only 1,458 facets. And we want to project this hypercube down to the R3. And we will see that the number of inequalities to describe this projection increases dramatically. But of course, the number of vertices is reduced. Okay, this is our projection. Here's the hypercube. We want to define such a linear mapping by a corresponding matrix. And this matrix is defined in this way. We choose 9 integer numbers from -4 to 4. And we put all arrangements of these of columns of these 9 numbers in a matrix. So we have this matrix with 3 rows and 729 columns. And after applying this, we obtain this polyhedron, and this has 26,187 facets, so much more than the facets of the original hypercube. So this is a defect that projections is nothing what is trivial. It is we have to do something. We have to compute something when we want to compute projections. Okay, and in a paper from 2016, we formalize this problem to project a polyhedron. We call this a polyhedral projection problem, PP, and we consider a problem in a similar notation than an optimization problem. So we have here linear constraints, and M can be seen as a kind of objective mapping, but we do not minimize or maximize, but we compute this polyhedron in some sense. And one can introduce a solution concept in a manner of optimization. I do not want to discuss the details here, but roughly speaking, solving this problem means to compute a V representation of such a given polyhedron. So we want to compute the vertices and the extremal directions at least. Okay. And now we can consider a corresponding vector linear program. I use the following notation. I say vector linear program if an ordering cone C is involved, and in case of the trivial ordering cone, I say multiple objective. This is my convention here. So we have the same constraints here. We have this objective map, this matrix here, and we minimize with respect to some cone. The feasible set is this set. This is clear. The ordering cone is assumed to be polyhedral, can be given by a matrix set here. And what is very important here is the concept of upper image. So the upper image is the feasible set. Then I apply the objective mapping to the feasible set. This is sometimes called the image. And then I add here also the ordering cone, and then I call this upper image, this set. So we see here the upper image can be expressed in this way. And this is, of course, a P representation of a polyhedron. So the aim, okay, and now I had also several papers on solution concepts of vector optimization problems. And also, of course, there are different approaches in the literature, but the solution concept I use here is the following. Solving this problem means, or roughly speaking, means to compute a V representation of this set here, of this upper image. Right, so we start with a P representation and want to compute a V representation. The same thing like in the polyhedral projection problem. We have given a P representation and want to compute a V representation. So as I said, multiple objective, MO means the standard ordering cone. So here is an illustration what the solution concepts means. I don't want to give a formal definition, just the idea here. We use this data for our problem, and S is the feasible set here. And using this mapping here, I obtained the image of the feasible set by the set which is bordered by this dashed line here, M of S. So the feasible, the objective mapping is a rotation by 45 degrees and a scaling. And then I add the ordering cone, which is the R2 plus here, and I obtain the upper image, which is this set here. So what we want to obtain, roughly speaking, is the V representation of this upper image. This is given by these two vertices, or one V representation is given by these two vertices and these two extremal directions. But the solution concept is not in the objective space, but as usual in optimization in the origin space. And what we define as solution is for every vertex or for every point here, a corresponding point in the feasible set. For every direction here, a corresponding point in the feasible set, with one exception. This blue extremal direction is not interesting for us because it belongs to the ordering cone, and we don't need some corresponding direction in the feasible set. So that means a solution of this multiple objective linear program consists of two feasible points and one feasible direction. And your usual notation is here S poi for points and S dir for directions. Okay, so given a polyhedral projection problem in this way, then we can assign a corresponding multiple objective optimization problem. What is this problem? Let's first look at the constraint. Here we have linear constraints and we use just the same constraints. What is the objective map? So here we have this matrix M, and here we have, or MX is the objective map, and here's also MX, but there is one additional component, minus the all one vector transposed MX. So the idea is the sum over all components here is 0. That means all these points here belong to the hyperplane all one vector transposed x equals 0. And then in a technical form, the result can be formulated like this. If the given projection problem is feasible, then a solution of the corresponding, of the associated multiple objective linear program exists, and every such solution of this multiple objective linear program is also a solution of the polyhedral projection problem. That means we can solve a multiple objective program to compute projections. And here I prefer to use a more informal formulation of the same idea. H is this hyperplane I already mentioned. So these vectors here belong to this hyperplane. And pi is the projection from RQ plus 1 to RQ. That means we delete the last component of the vector. And calligraphic P is the upper image of this multiple objective optimization problem. I said this is what we usually compute. And now I just have to intersect this upper image by this hyperplane, and I have to delete the last component, and then I recover the originally given polyhedron P. And in this way, I can compute projection by using a multiple objective linear programming solver. Here is an illustration of this idea. Imagine we are given this polyhedron here, a very easy one, an interval, and assume that we do not know the vertices of this interval. We are given this polyhedron in a projection representation. That means we know that this is the projection of some higher dimensional polytope or polyhedron. So the idea here is to add one dimension. So this is this hyperplane H here, and adding this dimension, we obtain this green Z here. And then we add the ordering cone R2 plus to this set. And this is the upper image of a multiple objective linear program. So then we solve this linear program and we obtain these vertices here and corresponding points in the feasible set. And this is the solution. That means we obtain a vertex representation of this green set, and deleting the last component of the vectors, then we have a V representation of our originally given set. So this works also in higher dimension, and this is the main idea of this talk. This idea can be done in the polyhedral setting as well as in a convex setting. So let us start with a vector linear program. This is the opposite way, and we can associate the corresponding polyhedral projection problem. So what kind of polyhedron is it here? This is just the upper image. This is a P representation of the upper image of this VLP. And this means we have also the opposite result, a solution of VLP of the given multiple objective or vector linear program, if it exists, can be obtained from a solution of the polyhedral projection problem. This means that both problems are equivalent, and even more, we have this connection here. This means in order to solve a polyhedral projection problem, we can use a multiple objective linear programming solver, and we have to add one more dimension, or have to increase the dimension by 1. So by the second theorem, we can solve vector linear programs if we can solve polyhedral projection problems. And of course, multiple objective linear programming is a special case of vector linear programming. Just use the natural ordering cone. And this also extends the classical results for the connection between MOLP and VLP, because in the classical result, it was known that both problems are equivalent, but the dimension of the MOLP here was not only one more than the dimension of VLP. In the classical result, the dimension here corresponds to the number of generating vectors of the ordering cone. And imagine we have, say, in R3 an ordering cone which has, or the dual of the ordering cone is relevant here. The dual of the ordering cone. And imagine we have an ordering cone where the dual has many generators, then our MOLB in the classical result has a very high dimension, very many objective functions. And now we have only one objective function more with this result. Okay, now I want to speak about approximation. Polyhedral projection, of course, can be solved exactly by finite algorithms, but sometimes outer or inner approximations are sufficient, and sometimes they are also easier to obtain. And for some applications, approximations of these polyhedra are already sufficient. Multiple objective linear programming is one example. Another example is parametric linear programming. This is also equivalent to polyhedral projection and to multiple objective linear programming and so on. There are classical papers about this. And also for the computation of reachable sets, it would be sufficient in the most cases to use approximations of the polyhedra. And here is some excursus to such an application, reachable set. If we consider a system of differential inclusions, the x prime is an element of f is a set-world map here of this f of x t t. Then we use this assumption here for all t in this time interval. We assume that our set-world map is polyhedral convex. This means that the graph of this set-world map is a polyhedral convex set. And this can be generalized here to convex sets. And we have the same application also for the framework of convex projection or convex multiple objective optimization. So here it is formulated for the polyhedral convex case. So then the graph is, as I said, a convex polyhedron, and the graph can be expressed in this way by linear inequalities, and the data here depend on, or can depend on the time. This is no problem here. So then we discretize this problem. We use here a fixed step size, we have a time discretization, and we have also a state discretization. And then we make the usual approximation for the derivative by the difference quotient. And after all this discretization, we obtain this discrete system. These variables here are element of this set-world map. And this can be formulated by using the formula for the graph of our set-world map by linear inequalities. And now we see what we obtain here is a projection problem. We are interested in the state variables at final time capital T, and all the other variables should be eliminated. That means we have a very high dimensional polyhedron, which is projected down to a lower dimensional polyhedron. So if you make some assumptions, say the data here have a fixed number of rows, say m, then we can say something about the dimension. Then we have d times capital N variables and
Andreas, excuse me. There is a question in the chat. May I read it? What is typical algorithm for solving MOLPs?
Oh, I will come later to this point.
Okay.
I will show an algorithm later in my talk. Thank you.
Sorry for interrupting. Sorry.
No problem. So, okay. So to summarize this, the reachable set of such a dynamical system is obtained can be done approximately by eliminating variables or by projecting d times n-dimensional polyhedral convex sets onto the RD. Here is another application of polyhedral projection, and because of the equivalence, also an application of multiple objective linear programming. This is called Polyhedral Calculus. The aim is to compute, for instance, the Minkowski sum of two polyhedra. And the idea is we start with P representations of the one and the other one, P and Q, and we want to compute this Minkowski sum here. And now the observation is that it is very easy to obtain a P representation of the Minkowski sum. So we can write down this immediately. The P representation of the sum is this one, and we have to take this composed matrices and composed vectors here. So the actual work is to compute a V and an H representation from this P representation. That means the only thing what we have to do is to solve a polyhedral projection problem. For instance, if we want to plot this polyhedron, we need to know the vertices and the inequalities. And with the same idea, we directly obtain P representations for intersection, Cartesian product, image under linear transformation, and inverse image under linear transformation, also a recession cone, and many others. And we can extend this idea when we start with a polyhedron and we ask for the polar of this polyhedron. This is the definition of the polar. Then we can use a form of the Farkas lemma, which is called Modskin's transposition theorem, a generalization of the Farkas lemma. And using this, we obtain immediately an P representation also of the polar. I do not show the formula here, it looks complicated, but it's just a simple application of Farkas lemma. And by using this Farkas lemma or Modskin's transposition theorem, we also obtain polar cone of polyhedron, normal cone of a polyhedron at a point, cone generated by a polyhedron, and also the closed convex hull of the union of finitely many polyhedra and other things. That means projection is the key computational tool for this polyhedral calculus. And we implemented a MATLAB and Octave code and we realized this idea in this tool, Benzoff tools. Benzoff is our solver for multiple objective linear programming, and we use this multiple objective linear programming solver to realize these polyhedral calculus operations in this tool here. Here is a list of other applications of polyhedral projection and also multiple objective linear programming, computing non-Shannon type information inequalities, and it uses this projection. Set optimization, set variable risk measures is one application. In global optimization, very similar ideas are used, and one also can use the multiple objective linear programming solver to solve certain global optimization problems. This is a kind of vector valued game theory. Then there is some application in algebraic statistics for computational biology, which is based on tropical geometry, and tropical geometry is based on some calculus rules for polyhedra. And also quantifier elimination is one application. And this is a list of methods which can be used for solving projection and also multiple objective linear programming. So very well known is the Fourier-Modskin elimination. usually formulated for projection problem. Of course, one could do vertex enumeration in the origin space and then compute the projection of the points. But when you think when we see our example with a green big polyhedron, you see this is not possible. There are too many vertices in the origin space. And there is a method called block elimination, which is related to this. This, I think, is kind of dual method. In some situations this works, but not always. What we used in our solver is a Benson algorithm. I will later show what the idea of this algorithm is. And we also established a dual variant of Benson's algorithm. And now when we know this connection to polyhedral projection, one can easily see that the idea, for instance, of the dual variant of Benson's algorithm is the same as the convex hull method for polyhedral projection, which was established much earlier. And another type of algorithms is a parametric simplex method and adjacent facet iteration. The idea here is that the simplex algorithm is generalized and one goes from one vertex to the neighbor or from one facet to the neighbor and so on. And this is an illustration of the primal Benson algorithm, and this algorithm also works in the convex setting. Here's an illustration for the polyhedral setting, and the convex setting is similar. One can formulate this algorithm for the multiple objective setting or for the polyhedral projection setting. Both is similar. Here I use the multiple objective setting. S is our feasible set. We apply the objective map and we want to compute this polyhedron, the image, but actually we only need to know the upper image. We add the ordering cone here. So the goal is to compute the vertices of this upper image. For the moment, we only know a projection representation of this, but what we can do is we can solve linear programs where the set here is in the constraints. So the first idea is that we move this blue hyperplane to the left, obtain this point here, and then this half space defined by the blue set is an upper approximation, and this red set here is an inner approximation of our set. And now we improve this outer and inner approximation. In our algorithm, we use the next hyperplane, move it down, obtain this point, and here for the outer approximation, we compute this point here by vertex enumeration, and in the inner approximation we compute the convex hull plus cone of these 2 points. And now we choose some vertex of the outer approximation and we go into a fixed direction here. When we want to discuss a polyhedral projection variant of this algorithm, we can also choose an interior point here, and we go from the vertex here to some interior point. Here in the vector optimization variant, this direction can be fixed. So then by solving a linear program, we obtain a boundary point here, and by solving the dual linear program, we obtain a supporting hyperplane, and then we cut off the vertex using this supporting hyperplane, and we have a better outer approximation. And we also have this point, we can update the convex hull here, and we have an improved inner approximation. So now we can think about approximation variant. We choose a vertex here, and we can ask how far is the inner approximation from the outer approximation. Now, what is the distance here? If it is small enough, we can stop, and then we have an approximate variant. Also, if we start with the convex set, we need to stop after a certain tolerance is obtained. But in the polyhedral setting, we can also solve the exact problem. So now I continue here with the same idea, and after finitely many steps, I have an inner and outer approximation, and I also have a V and also an H representation of this upper image. So now I come to the next level. I want to say something about spectrohedra. What is a spectrohedron? Our data here are matrices, symmetric matrices, L times L matrices. And we define an ordering relation by the cone of positive semi-definite matrices in the usual way. And the spectrohedron is defined as a vector a vector y, such that this so-called linear matrix inequality is satisfied. Because this is a linear matrix inequality, we sometimes also say the spectrohedron is also called linear matrix inequality representable set, LMI R set, for instance. And of course, every polyhedron is also a spectrohedron. In this case, we have to use diagonal matrices here, but spectrohedra are more general. Here is an example. The elliptope. Here we use these four matrices here, and we have this put it into definition. And here is a more compact way to express it. This matrix should be positive semi-definite, and here is the image of the elliptope, and here is the polar of the elliptope. Maybe this helps to visualize this convex set. And of course, this is a polyhedral approximation and not the original elliptope. The elliptope is not a polyhedron. Okay, first observation, when we deal with spectrohedra, let's look at this example. The disk in R2 is a spectrohedron by this representation here. And of course, also a line segment is a spectrohedron because it is a polyhedron. And now we can form the Minkowski sum of both and obtain this set. And we know that this set has non-exposed facets here. So this facet X bar is not an exposed facet. I do not find a supporting hyperplane such that the intersection of the supporting hyperplane and the set consists of only this point X bar. And then there is a result in the literature saying that every face of a spectrohedron is exposed. This shows that the Minkowski sum of two spectrohedra is in general not a spectrohedron. So the situation is different here from the polyhedral setting. What we can do is to introduce something what we called P representation in the polyhedral case, and which is called spectrohedral shadow in the spectrohedral setting. This is the same idea. We have a linear matrix inequality here in the variables X and Y, and we project it down to the Y variables. A spectrohedral shadow is also called semi-definite representable set or SDR set. And of course, every spectrohedron is also a spectrohedral shadow. Just we can use here, or is not said that the B matrices must occur here. And now we find a result in the literature that the family of spectrohedral shadows has nice properties when we think about calculus rules. It is closed under several operations. Here is a partial list of these operations. So the Minkowski sum of two spectrohedral shadows is again a spectrohedral shadow. Intersection, Cartesian product, conic hull, convex hull of union, affine image, the inverse affine image, the polar, the closure, and also the relative interior. At this point, I should say that a spectrohedral shadow is in general not closed. And therefore, this closure operation makes sense here. Okay, that means in the framework of spectrohedral shadows, we have a similar setting like in the polyhedral case. We could think about such a spectrohedral calculus. And now we want to come back to our main idea. We are given a problem, a vector optimization problem, a vector semi-definite program, and we minimize a linear objective mapping here, and the constraint set is a spectrohedral shadow. So it is important to realize here that in this term spectrohedral shadows, many variables can be involved, even even if X has a low dimension, we can have much more variables here. When we, at the end, we have to write down the matrix, the linear matrix inequalities, and have additional variables here. So S is a spectrohedral shadow, as I said, and the ordering cone can also choose an S as a spectrohedral shadow. Should be a cone, of course. And then we can define the upper image. This is defined in the same way as in the polyhedral case, but here usually we take the closure. And we know that the upper image is again a spectrohedral shadow. And now we can proceed analogously to the vector linear programming case. We can compute approximal primal and dual solutions of this vector semi-definite program. And these are closely related to inner and outer polyhedral approximations of this upper image here, which is a spectrohedral shadow of a special form because we have this ordering cone here involved. And now we can apply the same idea. We are given an arbitrary spectrohedral shadow and consider the associated multiple objective semi-definite program. It's the same idea as in the polyhedral case, but just a simplified notation, because in this term spectrohedral shadow here, a lot of inequalities and additional variables are hidden. So we have here Y, and we add the components such that the sum over all components is 0. And now we can compute an outer approximation of the upper image of this multiple objective program. We denote it by P outer. And then we use the same idea. We define this hyperplane H, and pi is the projection, which means deleting the last component. And what we obtain is an outer approximation of our originally given spectrohedral shadow. That means we can compute polyhedral approximation of spectrohedral shadows by solving a multiple objective, or by approximately solving a multiple objective semi-definite program. And now we can replace everything what is related to spectrohedral shadow by convex sets and semi-definite program by convex program, and we obtain the same result also in the convex setting. But the disadvantage of a formulation in the convex setting is that the projection idea gets lost here a little bit. So here we have this shadow, and I mentioned several times that additional variables are hidden here and so on. And when we write down a convex set here, we sometimes forget that actually we have or in many cases, when we represent convex sets, projections are involved. So now we have the same for the convex setting. Everything's the same. And now we can go to proceed with an error analysis. So when we do this reformulation of convex multiple objective programming and approximation of convex sets or convex bodies, the question is, what about the approximation error of the one problem and the other problem? So we're given a convex body K in our Q, and we assume that our solver can handle constraints of the form Y is in K. This is all the point where I said here the projection idea is involved. And then the associated multiple objective convex program is this one. And this can be solved approximately by using, for instance, the primal or dual Benson algorithm. I have shown the idea of the primal Benson algorithm, and the dual algorithm is very similar. We just have to translate the idea of the primal algorithm to a polar setting. So we can consider the dual problem of the vector optimization problem, and instead of the upper image, we have some other set which is in a kind of polarity relation to the upper image, and we apply the same idea to the polar, and in this way we can translate the idea, and we have a very similar algorithm, and the one computes outer and the dual computes inner approximations. But it is enough to discuss all the things here with the primal algorithm and outer approximations. But the error analysis works for both. So we assume we solve this problem by the primal or dual Benson algorithm, then we usually have a prescribed tolerance epsilon. And the question is, what is the approximation error of the corresponding polyhedral inner or outer approximation of the given convex set K? So and the answer was found in these two papers independently. When we have a tolerance epsilon, then for the upper image and its approximation, we obtain the following bound for the Hausdorff distance between the upper image and its polyhedral approximation. It's epsilon times square root q plus 1. So, I mean, this is a technical thing that it depends on the reason is the formulation of the Benson algorithm that we have this bound here. We also could formulate it in a different way and could say that, and such that we start with the epsilon here and not epsilon times something. Okay.
So yeah, somehow didn't get what was Q?
Q is the dimension. Q is our convex body is in dimension Q.
Okay.
So and now we use this procedure I have shown above to approximate the convex body, and then we obtain this Hausdorff distance between the convex body and its polyhedral approximation. It's bigger. The ratio of both is this one here, which is smaller than square root q. So roughly speaking, there is the factor square root q bigger the approximation error. So this is not so nice that we have a bigger approximation error, but on the other hand, it's a moderate increase. If usually the dimension is not so high here in problems what we can solve, and so let's say a moderate increase. And at the end of my talk, I also would like to discuss some classical approaches to approximation of convex bodies, and I would like to relate this a little bit to what I presented here. So in a series of works by Kamienev, we find two approximation schemes for convex bodies and also a very interesting convergence analysis for this. The one is the augmentation scheme for a convex body K in RQ. So, which is described here. We choose a point Y on the boundary of the convex body, and then we construct the new approximation from the old approximation convex hull with this boundary point. And the second scheme is the so-called cutting scheme for a convex body. Here we choose a direction on the unit sphere, and the new approximation is constructed from the old approximation intersected by a half space, and this half space is computed by using here the support function. So this is a supporting half space to K. And now we see that this cutting scheme is nothing else what we did in Primel-Benson's algorithm. Means Primel-Benson type algorithms is the same as the cutting scheme. So the one is usual. The one term is usual in multiple objective optimization, and the cutting scheme term is common in the framework of approximation of convex bodies. And the dual Benson algorithm is nothing else than this augmentation scheme here. And in both worlds, we use different notations or different terms for these for the same idea. A nice survey of all these connections here, also about the convergence analysis, can be found in a recent PhD thesis of Chiripoy. And this is my last slide. This is also some other idea what was studied in the thesis of Daniel Chiripoy. We could also think about the idea to compute spectrohedral approximations of spectrohedral shadows. We know that a spectrohedral shadow is not a spectrohedron in general, and we could try to approximate a spectrohedral shadows by linear matrix inequalities here. And this works. So one can formulate a semi-definite program, and in dependence on the matrix size of the semi-definite program, you obtain a polyhedral approximation for very small matrices. And if you increase the matrix size, you obtain a non-trivial or non-polyhedral spectrohedral approximations of spectrohedral shadows. So for me, it was very interesting to try is such an approach possible. The final result of this thesis is that this is our view on this topic, that it is not very so it is difficult to realize in practice. So it needs much more time to compute a spectrohedral approximation than a polyhedral approximation. This is one negative aspect. And another one is that it was not possible so far to get an error approximation better than for a polyhedral approximation. So that means we can see on the pictures that the spectrohedral approximations are better than the polyhedral ones, but we cannot prove it. So for an example, what we cannot draw, we have no error estimation. And this is maybe the main drawback so far. We do not know if such an error approximation is possible or not, but we did not succeed to show one. So this is the end of my talk. I have I have conclusions here. So my conclusions are that polyhedral approximation of a convex bodies is equivalent to approximately solving multiple objective convex programs. We have seen that we have a moderate increase of the approximation error when a convex body approximation is derived from an associated multiple objective convex program. But in practice, I would prefer the opposite way. We should implement and develop algorithms for convex body approximation and convex set optimization and use them to solve multiple objective convex programs, or also on other levels, say multiple objective semi-definite programs, because the advantage here is that we have no increase of the approximation error, and another advantage is that we have not this increased dimension, that the dimension does not need to increase by 1. But the treatment of unbounded convex sets and unbounded spectrohedral shadows is still challenging. In the bounded case, everything is nice and easy, but of course, also the unbounded case is interesting, and this is a recent PhD project by Daniel Dörfler. And then I conclude my talk with several slides on the references I have shown here in the talk. I thank you very much for your attention.
Thank you. Thank you, Andreas, for this beautiful presentation with interesting connections. And I suspect that we are going to have a discussion, aren't we? Bruno, please go ahead.
Oh, hello. Thank you. That was a very interesting talk. I think I have a couple of questions. So first, in the LP case, if I understood correctly, you can, in a sense, claim that you solved for example, the multi-objective linear optimization problem. If, for example, you got the vertices and the directions for the upper image or something like this. But in the case of spectrohedral shadows and multi-objective semi-definite programming, these sets are not polyhedral. So you can have, say, infinite number of vertices and so on. So I just wanted to understand a bit, what does it entails to say, yeah, what does it mean to actually solve this problem?
In the framework of spectrohedral shadows and convex sets, I only speak about approximately solving. So
okay.
That means we on the project, on the side of set approximation, we aim to find polyhedral approximations of the sets, and on the side of optimization, we want to find approximate solutions, and these approximate solutions correspond to polyhedral approximations of the upper image, though they're actually the same idea. And of course, in theory, one can also define solution concept in using this idea for the original problem, but as you said, infinitely many points and directions are involved then, and this is not possible to implement.
I see. Okay, so I guess when you have multi-objective, so I was going to ask about algorithms for directly solving the multi-objective STP, but as you said, that's not typically the goal. So it's more just to get polyhedral approximations. So, okay, but I think I'm going to ask this anyway. Is there any algorithm to solve the multi-objective STP? And by solve, I don't know, for example, just get some points. I'm not sure if in this case can talk about Pareto frontier or something like this. But, you know, to get a piece.
We must be careful when we speak about solving a multiple objective program, because there are different concepts in the literature. Some people say solving a multiple objective problem means to compute one efficient solution or one Pareto efficient solution. Others say we want to have all Pareto sufficient solutions. And the concept I use here is something in between. We want to know the Pareto frontier in the objective space and corresponding origin points. So, and when I say polyhedral approximation, I speak about polyhedral approximation in the objective space and corresponding description by objects, points, and directions in the feasible set. So maybe this is sometimes confusing that there are so many different concepts in the literature.
Okay. Thank you.
Okay. There have been several apologies from people who are leaving, in particular from Jordan Rufa and Hua Bao. They had to leave because of other meetings. So we have a question from Gary Newsom. Please, Gary.
Yes, Andreas. I'd like to ask a sort of inverse problem question associated with this. So early on, you gave that example of a projective polynomial, which is a relatively small number of high dimensional facets, but projected down to a large number of lower dimensional facets. But presumably the projection matrix and the higher dimensional characterization are relatively small compared to the number of parameters needed to specify it in the low dimensional facet case. And so I was wondering if there's some way of, given a complicated sort of polyhedron, that you can find a relatively simple, but maybe higher dimensional representation of it. And to take that one step further, maybe you can find a sort of a simple high dimensional representation, which is an approximation to this more complicated lower dimensional one.
I can only say that in combinatorial optimization, this is a usual technique to go in a higher dimensional space to get an easier representation, to reduce the number of inequalities, for instance, for combinatorial optimization problems. This is called lifting there. They lift the problem to make it easier. I don't know anything about approximation or this combined with approximation. I cannot say anything.
Do you know if there's a sort of general lifting strategy for, given a...
I'm not an expert in this topic, so I just know it is used there, and it's a real difficult topic. So.
And also you don't know anything about, you mentioned this issue of approximation of polyhedrons. And again, presumably, if you could find a lifting and a projection that was close to your original, but much easier to work with, and had some measure of how close it was, would be useful, I guess, in some situations. And I'll leave it there.
I can't say more to this.
Thanks.
To this topic.
More questions, comments, please, Janusz?
Yeah, I have one question. Can you go back to the differential inclusions?
Sure. So here.
Yeah. Okay.
I think it was the first slide, or yeah.
Yeah. So what is this? So they are. Okay. So the matrices depend on time only. Okay. Yeah. Then I understand what's going on, because otherwise it gets very complicated. I mean, even if it's polyhedral, if it depends on X also, it gets very complicated. And so what I would think is, I mean, I have seen your papers on this, maybe 5 years old or so, maybe 6 or 7, I'm not sure. But now that you are also working with more general classes of sets like Spectrohedral and so on, do you think it would be possible to capture more interesting classes of differential inclusions? Because now you have a bigger toolbox.
You mean non-polyhedral inclusions here?
Yeah, or let's say something that depends on the space parameter in a non-trivial way. So let's say in a linear way, or yeah, so where the x plays a role as well.
No, I have no idea. What I know from the literature is also this polyhedral setting here, or
yeah.
And I just mentioned that we could do the same, but I'm not expert on this differential inclusion, so and I have no idea if there are examples where the set here is convex with respect to x.
Yeah. Okay. I want to ask something else. This Modskin's transposition theorem. What is that?
This is an extension of Farkas lemma. The idea is that in the usual classical Farkas lemma, you start with a system of linear inequalities of a special type. So you have usually ax greater or equal than b. And in the Farkas lemma, you have all types of linear inequalities. You have equations, inequalities, and also strict inequalities, and a corresponding result.
That looks similar as what we know from Farkas.
This is actually, you prove it by Farkas lemma, but this is a generalization, and it is easier to apply in situations. You don't need to transform everything to the classical Farkas. You can directly apply the Modskin transposition theory. It can be found in the book by Güler, for instance.
By whom? Güler? Güler?
Güler, yeah.
G-U-L-E-R?
Yeah, I think Foundations of Optimization also is the title.
Okay, well, then I will have a look. Thanks.
I don't see any more raised hands. Does anyone want to ask a final question? No. Okay, thank you very much, Andreas, for your presentation, for agreeing to join our seminar. This is always great to have people from Europe, especially experienced people in this area. So thank you everybody for joining this seminar. And
thank
the
you
next
also from my side.
Great. And the next one is in 2 weeks, same time. See you then. Okay, thank you.
See you. Bye.
Can we stay behind for a moment? Is that okay? I mean,
yes.
Sure.
Or
whom do you want to stay?
It doesn't matter. I just want to ask some stupid question that maybe nobody's interested in.
So a question for 8 people. Okay.
For Andreas. I just wanted to ask. I mean, when you approximate, do you still have a few minutes, or are you on the run?
Yes, I have.
Okay.
Yeah.
When you, I mean, I'm not sure whether I understood this. I mean, when you want to approximate a convex set, then you have such a blob there, and you want to such a blob like Klex. You have some shape there, some round shape, let's say, and you want to approximate it, and then you. Because when I think about it naively, then you have this blob, this Klex thing, and it's not clear to me when you then start your cone business. Aren't you missing the backside of the blob? Or did I skip a lifting argument or something like that?
So you mean that? Let me show the corresponding picture.
Mm-hmm.
I mean, is everything the same in the polyhedral case?
Yeah.
This is the counterpart for your set, right?
Yeah.
And but I do not add here the cone, but first I go to one dimension higher and then I add the cone.
Yeah,
right?
but what do you do there?
Set,
when you go one
no
dimension
information
higher?
is lost from the set.
Hmm?
So when I understood your question correctly, then you have the idea that this green line here is the set, and then I add the cone, or maybe this is not good, this example. So I have such a set, and when I add the cone, I lose information, right?
Yeah.
So some part of the boundary is still in the new set, but backside is not.
Yeah.
So, but what you do here, you have this disk, then you first go to dimension 3 and add the R3 plus cone to this set. And then your disk is one facet of a 3-dimensional set.
That is your last
no
row
information
of
is lost.
This is the last row that you attach to your problem. Is that
yes,
correct?
Yes, this is last row.
Okay, that is that. So you first lift it up by attaching that last row, which you can always
the main
do.
idea of in the lower dimension you have an arbitrary set, and this corresponds to a special set in one dimension more. And this is reversible, this idea, right? If you have a special set in a higher dimension, you can.
Yeah, I think I missed the key point. But okay, I think
the problem is that it would be better to explain this in one dimension more here, this idea, but I was not able to make a good drawing of this.
Yeah, but it's fine. I mean, now I understand. I just didn't make the connection between the last row of this augmented system and this tilting the interval. Okay, thanks. Yeah, then I begin to understand, because I have seen way back at some conference, I've seen similar pictures, and I already didn't understand them there, and I thought now I want to understand them finally. Okay. Yeah, thanks then. I mean, we are already in unofficial territory now, I think. Yeah.
You have a group of 6 chosen people. Enjoy the discussion. Okay, so if no more.
Sign of life from Juan.
Well, likes this. Okay, thank you very much. I'm closing it. Probably it's up to Juan to close it.
Yeah.
Anyway, see you later.
Okay, see you all.
Okay,
Thank you.
see you. It was nice to meet you.
Yeah.